Okay, so this is indeed great that so many people came. This is what I call community. This is great. Yeah, so some guy, random guy like me gives a talk and still 70 people show up. This is great. So I would like to start to strengthen this community a little bit. So let's do something that we've never done before. Look to your left neighbor and talk to this left neighbor. Say to him something like, it is great that today I'm spending this evening next to such a professional, such a motivated C++ developer. So, see? Okay. So, you can introduce yourself later properly. So, then of course you should reply, yeah? So if somebody's that nice to you, you should of course reply. So now take a look at your right neighbor and tell your right neighbor, oh, thank you so much, I like myself too. So today's topic is a topic that you probably cannot really relate to. So no paradigm programming, what is that? This is something of a bigger question that I'm asking myself a lot. This is what I'm thinking about. This is also what I'm asking C++ trainings. Okay, we forget about this one slide. What is C++? This is actually a pretty tough question, is it? And there has been a talk entitled with What is C++ at CPPCon 2019, a talk given by two relatively prominent persons, Chandler Carruth and Titus Winters. These guys should know. And still, although it was a great talk, it was not a definitive answer. So it is a really tough question. So I really recommend the talk. It is a very good talk, but you will not get the answer, unfortunately. However, I'm personally not just interested in what is C++, a tool or something like that. I'm also very much interested in what kind of programming language is C++. And this is something that is a particularly difficult question if you give a C++ training. How do you explain to somebody what kind of language C++ is? And the most obvious answer to this question is, of course, it's an object-oriented programming language. This, surprisingly, is an answer that you get from approximately 70% of people. Yes, Roland, 70%, I measured. And one evidence is, for instance, in this book, Code Complete, pretty well-known book. And it summarizes a couple of programming languages, amongst others C++. C++, an object-oriented language founded on C, blah, blah, blah. And there's more evidence. So perhaps you know learncpp.com. Tutorials to help you master C++ and object-oriented programming. So of course, a beginner is very, very convinced right now that C++ is an object-oriented programming language. And there's more. So just last week, in the newest episode of CPPcast, Brett Larson, which I don't want to pick on just as kind of an evidence, said, overall, you can get up running pretty quickly with an object-oriented programming language like C++. This is kind of an answer that you get quite a lot. However, this is not really what the community thinks anymore. The first, first, why is this perhaps a prominent answer? Well, indeed, C++ was inspired by Simula. And Simula is the language that introduced objects, classes, inheritance, virtual procedures. So after all, Simula is indeed an object-oriented programming language. And so it's kind of clear that from this heritage, it should be object-oriented too. However, due to other talks, we realized perhaps this is not the entire truth. You might know this talk. If you don't know, watch it. It is just about 24 minutes. It actually was so good that the guy could run over by 5 minutes. Inheritance is the base class of evil. He's hitting pretty hard on object-oriented programming. In the first 10 minutes, he's basically telling us this does not work. We at Adobe, we did not like it. We replaced all these inheritance hierarchies, not all, many of these inheritance hierarchies by something else. And there's more evidence. So just last year at CPPCon, there was a talk, Back to Basics, Object-Oriented Programming. And you go to the talk, would expect that somebody finally talks about C++ anymore. But no, John Cobb starts with, I know you didn't expect this talk at CPPCon. Nobody nowadays talks about C++, about object-oriented programming anymore. And he starts with a slide that is really, really negative. Why are so many developers hating on object-oriented programming? there's apparently a pretty negative attitude towards object-oriented programming in C++. And some guys even overrate this, go higher, OOP is dead. Okay, this is probably too much. This is probably a title that was supposed to sell this talk, but really negative. Instead, what people talk about much more often is, like Sean Parent talks about functional programming. So this is also a talk that you might know, C++ seasoning. He tells us that we should use raw loops, that we should go in the direction of functional programming. This is talk that you might know. Jonathan Pecara, he says, well, algorithms, functional style, this is the right thing to do. There's more. Connor Hoekstra, also a talk that I found pretty entertaining, also about C++ algorithms. And there's other talks like Kevin and Henny, who talk about functional C++. And if functional C++ is not enough, there's also functional C++ for fun and profit. Yeah, of course. Apparently, the opinion is divided. Object-oriented programming, functional programming. If you go to Wikipedia about C++, well, Wikipedia clearly says multi-paradigm, procedural, functional, object-oriented, and generic. It's just all of it, which is not really a satisfying answer, though. So I'm now asking what kind of program language is C++ really? So before we get started, it could be procedural, object-oriented, functional, generic, multi-paradigm. You got the point. So I now want to go into this question by example. I want to see how we today solve common programming problems. And of course, well, as a disclaimer, C++ is really complex. You can also not expect a definitive answer this evening, unfortunately. But perhaps I can give you a couple of more keys to this big puzzle. I also only consider solutions that use dynamic polymorphism. As soon as you say dynamic polymorphism is not interesting for me, the solution space is even wider. I will show you 7 solutions in total, which I believe for 60 minutes is already quite challenging. We'll see if this works out. There will be a lot of code, unfortunately. So I've never given a talk with that many slides of code, but it is not about the details. It is about the overall design. What I want to show is how we today address a problem, how we design in order to decouple things and come to better designs. Yeah? And I deliberately choose a particularly simple problem. So it's not a very complex one where we have to talk about 30 minutes to first describe the problem. No, I choose probably one of the simplest problems. You know, I am drawing shapes. We all, okay, before you complain, yeah, we all know how to draw shapes intuitively. It is now about how to design it properly under certain site conditions. And as I said before, we want to do this dynamically. So the first solution that comes to mind to draw a shape is a C-like procedural solution. So we start with, of course, an enumeration. In a simple example, I have circles and I have squares. Not a lot of shapes yet, but it's about design, as I said before. Then there is a shape class, a base class, that has one thing in particular that is perhaps a little awkward. It stores one of these enumerations, so it remembers what kind of type it is. In the constructor, I pass one of these enumerators, and from this moment on, it is fixed. The circle class, one of the possible shapes that I consider, initializes its base class with one of these enumerators. I'm a circle. I should remember that I'm a circle. Then, of course, a circle has a couple of more things. It has a radius, a center point, rotation, whatever. There's a lot of things. Data members, of course. And you can nicely deal with a circle by having a couple of functions. Note, the functions are not inside the class. It's not necessary. There's nothing I gain from putting them inside the class. This is kind of the procedural thing that we would do in a C-like environment. All right, not a big surprise, but just to have two. Square is very similar. It primarily initializes its base class with square and has a couple of different member functions. Yeah, so get side instead of get radius. Again, I can do a couple of things with squares. I can translate it, rotate it, draw it, whatever you like. Now, I am interested in drawing a lot of shapes, a vector of shapes. Nicely put into a vector of unique pointers, of course. Now, how do I draw a lot of shapes? Well, I iterate over all the shapes, and I'm asking, What kind of shape are you? Are you a circle? Well, in that case, I need to draw a circle, but I, of course, also need to cast a circle pointer. Or perhaps it's a square, then I draw a square, but cast a square pointer instead. Now, in the main function, I basically create a vector of shapes. So, nice type there first. And then I create a couple of shapes, a circle, a square, and a circle with radius, side length, and radius again. And finally, I simply draw all the shapes. Nice, this works. Let's take this as a baseline. You might think this is not a good baseline, but you will see in a second that is actually a reasonable baseline for a couple of reasons. So I try to evaluate a design based on 5 different categories. So how easy is it to add shapes? That's the first thing. Then how easy is it to add operations? And how separated are the concerns? So how loosely coupled are things? Now these 3 categories use abbreviations, OCP, SRP. Do you know them? Okay, just for the fun of it, let's summarize the solid principles. This is the 5, 2 of these solid principles are hiding here. What are these solid principles? What's the first one? Principle, correct, SRP. Then the next one is open close principle. So everybody who knows it gets a bonus point. Then the L is the Lister substitution principle. Now suddenly it's more people. Bonus points are interesting. Then the next one, the I is interface segregation principle. And last but not least, dependence inversion. So for us, mostly interesting are the first 2, but I'll come back to the other ones. This is good principles. If you don't know them yet, you should take a look at them. This is really design driving principles. So as a 4th rating, I rate for use simplicity. How easy is it to use the design? How easy is it to understand the design? And last but not least, of course, performance. We're interested in performance as well. All right. The enum approach is seriously bad in adding shapes. This is actually the worst thing you can do, adding a new shape in a solution. Why? So 1 is actually very bad. Yeah? So very bad is red and good things will be green. If you add a new shape, first of all, you have to attach the enumeration. This is a singular point of dependency. Everything depends on this one enumeration. If you change it, everything needs to at least recompile and potentially changes. And all the functions that deal with this shape type, for instance, a draw function that you saw before, need to be adapted, need to be touched. How do I find all the places that need to be touched? This is a serious problem. This is a maintenance nightmare. This is the designs that eventually just go wild and you do not have any guarantees anymore. So this is a definitive 1. Adding operations, however, is pretty simple. Adding free functions, you can add a free function to everything. So this works pretty easily. This is where this design is not too bad. Separation of concerns, well, there's still a couple of things that are mixed up. It's not nicely separated, so I vote for a middle value, somewhere in the range of 5. It is pretty hard to really entangle these things. Simplicity, also somewhere in the middle. You'll see it gets much, much simpler. For instance, in this solution, there's pointers, there's base classes. There's a lot of indirection. Let's vote it with 5. Performance. All right, performance. I have a couple of benchmarks. Now, before I show you the first benchmarks, benchmarks are tricky. Benchmarks are really tricky because usually it's somebody always complains. You cannot show benchmarks without somebody complaining. So, first of all, I am using the laptop here. So this is not something special. It's a MacBook Pro 13-inch. It has an Intel Core i7 with 2.7 gigahertz, 16 gigabyte of RAM. What I do is I create 100 random shapes. It's not necessarily 50-50, it's random shapes. And I do 2.5 million updates. Of course, I do this randomness cleverly. All the solutions use exactly the same setup. I use C+17 with O3 and dndebug as compilation flags. Nothing special. I'm not interested in special compilation. I'm just interested in a comparison. Okay, you promise me that you do not take this as the values, the single truth? Yeah? Okay, I take this as a yes. So, I say this is performance of 1. I normalize it too, because I want to compare things only, and it's just numbers. So GCC is exactly 1, and Clang was a little bit slower. However, as you see from the scaling of this bar, this is actually a pretty fast solution. It really is fast, surprisingly fast. And despite the fact that you now have the feeling, oh, this is a terrible solution, this is actually used quite a lot because of performance. The gaming industry, for instance, is using it, right? No. Question? 1 is good. Now, okay, 1 is good, which means less time. Good point. Yeah, I know. So, I would give it a full 9. From a performance point of view, this is a really, really good solution. And there is reasons that this is used today. Now, you don't like it. You don't like the fact that I have to add operations, that I have this enum. What would be your first thought when you see this design? What would you go for in order to improve it? What would you do in order to make it simple to add shapes? So we would go for a virtual function, right? That's what virtual functions are about. This is the right thing. So second solution, another approach. Now I go for virtual functions. Translate, rotate, draw. I know virtual functions, pure virtual in the base class, simply because I don't know yet what to do. This circle now properly implements these functions. Translate, rotate, draw, whatever's necessary, it is done here in the virtual function. Note, no more enumeration, of course. And a square class, same thing. I go for virtual functions. Translate, rotate, draw. Fine. Now, how do I draw a lot of shapes? Well, actually by just traversing the vector and drawing it. Suddenly this function is seriously simple. This function is something that I never have to touch anymore. This is what open-closed actually tells us. We should design things such that we do not have to touch them anymore. This is great. And in the main function, nothing changes. This is exactly the same setup as before. All right. An object-oriented programming solution. How would this compare to the enumeration? Addition of shapes works pretty well now. I rate this with an 8. It's not entirely easy. I have to do a lot of things here, but it is pretty good. Addition of operations. Oh, now this sucks. This sucks pretty badly. I wrote with a 2. I don't want it to be too bad, but now I've actually another solution which has inverted the problem. This is not 2 equivalent solutions. It fully depends on what you're actually aiming for. This is different. Now, from a separation of concerns point of view, I don't like it at all. The draw aspect is now finally really coupled to the implementation of circles, squares, etc. This is exactly what we should not strive for. Simplicity, I don't see a big of improvement from a usage point of view. It's virtually the same thing. It's also 5. Performance, well, it's a little worse. I was actually pretty happy that it's not much worse. It's a little worse, but still, this is the reason why very often people do not virtual functions. Approximately 30% overhead. So I rate it with a 6. So you see, it gets worse. Now, totally different solutions. Yes, of course, you might rate adding of shapes higher, so this is the solution you would like to go, but still, it's kind of the contrary. It's not equivalent solutions to the problem. Let's go back to the enum solution and let's try to find something that enables me to easily add operations, because this might be the thing that you're interested in. There's a design pattern that you can use that allows you to easily add operations. Which design pattern am I talking about? No. No. Visitor. The visitor design pattern. So in case you don't know it, I give you a quick overview. On the right-hand side, we have a hierarchy of elements. This is what the Gang of Four calls them. Call them shapes. So this is our shapes. There's circles, there's squares. These shapes, I consider them to be a closed set. I consider this to be the final number of shapes. There's nothing more to this anymore. This is actually a pretty important side condition, else the visitor does not work well. So all these shapes are existing, but they do not have all the operations that you could possibly have them. So I might right now have draw, translate, rotate, but I would like to add more operations. And as you've seen before, it is pretty hard to add operations to an inheritance hierarchy. For that purpose, I now introduce another hierarchy, the visitor hierarchy. The visitor is kind of an operation. Visitor, first of all, is a base class that now has a lot of possible derived classes. For instance, rotate or draw. This is my operations. And they operate on the known shapes. This is where this closed set comes into play. A visitor knows about all the shapes. There's a strict dependency on the complete set of shapes. Now, in order to make this work, a shape gets an accept function, traditionally. Accepts gets a visitor. The visitor is called in the according implementation in the circle or square class. And I move to the visit function, to the right one. So circle calls visit for circle, square calls visit for square. And so I trigger the actual implementation for myself. This is a pretty common design pattern because it solves a pretty important problem. But it does not come without problems. The first problem is that indeed the right-hand side needs to be a closed set. Seriously important. This is why I stress it a couple of times. And additionally, I now have two virtual functions. One virtual function here for the accept, one virtual function in the visitor. And you will see this is a serious downside. This does not pay off well. So first of all, an implementation overview. The visitor base class is defined first. I can visit circles and squares at this point. The shape base class does not have any other operations anymore except accept. Accept is the one that takes a visitor. Now the circle class is not changing a lot. I just get rid of all the other virtual functions. I only implement accept. That's the central function here. And square is essentially the same thing. The square also implements accept. And yes, they need the same accept function. It looks exactly the same, but it's the this point that is important here. So it's an implementation in every deriving class. Draw might be our visitor of interest. I want to draw all kinds of shapes. And I can visit both circles and I can visit squares. Draw, well, the draw function that traverses all kinds of shapes now simply has to call accept with draw. And this dispatches this particular visitor. All the shapes are nicely drawn. And again, I do not have to change anything in the main function. This is still the same. Now, how does the visitor compare to the other designs? Addition of shapes? Not so much. So I don't think it's as bad as the enum because at least I get a little more feedback. It's not a maintenance nightmare. It's a little better, but still, this is bad. Addition operations, pretty good. This is why I'm doing this in the first place. I give this square 8. It could be a little better, but still, this is pretty good. This is why people use the visitor. Separation of concerns, actually also pretty nice. The implementation logic of all these operations is no longer attached to the actual shapes. It's somewhere else. And this is a really, really good thing. This is why this design pattern also works pretty well. Simplicity. Okay, I see shaking heads. So the main function did not change, but when I talk about visitor, usually people don't really get it right away. It is, from a conceptual point of view, just much more difficult. I rate it down to 3. It's not terrible, but it is much, much more complicated than other designs. Performance, oh my, this is where it really badly hits us. The performance is, on my machine, on my setup, dropping by a factor of at least 2 to 3. So 2.5 for GCC and over 4 for Clang. Now, I don't say Clang is worse. This is just the results I got. The most important point is it is much, much more expensive. So I rate this down to 1. This is what we usually do not want to have. A slow solution. But of course, 8, the 2 8s, this is great stuff actually. Now, I said in the beginning that C++ is not really in the realm of OO anymore. A lot of people talk badly about object-oriented programming. And perhaps the red numbers here is an indication why they do that. And so the community tried to find another solution. An exact replica of this solution with the same properties, but better. Okay, a couple of you have an idea already what I'm talking about. What is better than a visitor? a variant visitor. All right, let's take a look at a modern C++ solution, the solution that I today would rate as state-of-the-art. The circle class is now a simple circle. There's not a single virtual function in this class anymore. It is just what you would show a beginner. Yeah? It's really a beginner's class. Square the same. No single virtual function, no pointers anywhere. It is the simplest square that I could imagine. Then an operation. Operations in a visitor are simply implemented by creating function objects. Objects that you can call with circles or squares, with all the things that a variant could be. And a variant itself, a class template that is specified to be either circle or square. It can be both. So variant is essentially a modern union. I don't want to go into detail here. It can be both circle or square, not at the same time though. It's exactly one thing. However, what is something that can be either a circle or a square? Well, this is a shape in our terminology. So the base class has vanished because I have something better now. I have a container that is able to do this abstraction differently. And drawing all possible shapes, well, you see one thing. Suddenly I have a vector of objects. I do not have a vector of pointers anymore. It's totally enough to just store the variant itself. Now, I traverse all the shapes and I visit it. This is part of a variant. I apply some operation on a variant. And this visit function magically comes up with the right thing that I currently store inside the variant, calls the right operation and does its job. The main function, okay, it's hard to show you anything that is simpler than this main function. All I need to do is now to create a vector of shape, variants. And I can push back circles, squares, and circles. I have to admit, this is still something that amazes me up to this day. You can suddenly add different things in the same vector. This is what we usually do not do, because you cannot do it. Now suddenly it's a thing. It's a good thing. So, how would I compare std variant to the so far seen solution? So, from addition of shapes, well, same problem as before. If I wanted to add a shape, I would have to touch the variant and I would have to touch all the operations. And this, of course, might have an effect on client code, and no, it's not easy. Addition of operations? Oh, brilliant. There's nothing better than this. You just write in your class with all the operations and you're done. It's the simplest thing you could possibly do. This is kind of perfect. It doesn't get any easier. Separation of concerns? Well, any kind of shape does not have to know about all these operations anymore. They're totally oblivious of whatever you can do with a shape. There's nothing better than this. This is perfect separation of concerns. Awesome. Simplicity? You liked it, right? It was seriously simple. Indeed, this is code that I can show in a beginner's training. Not on the first day, of course, but perhaps on the 5th day. Why not? People will understand it. It's not so hard. So this is as simple as it gets from my point of view. And performance? Okay, I would have liked to tell you this is amazing. But unfortunately, there's a hiccup. I expected this to be faster, but it's approximately twice as expensive as Daemon solution. Why is that? Well, the variant internally needs a little magic. And now you don't have to understand this code. I just point out a couple of details. There is some kind of table. So it's actually called table here. This table is an array of pointers, function pointers. And these function pointers are filled at compile time by a couple of lambda functions. It's not something difficult to do, but the variant might have an array of function pointers. And this array of function pointers means that there's an indirection. An indirection that prevents inlining, an indirection that actually costs on, so it's a little more expensive. The standard predict actually requires this kind of thing because it requires you to have an O of 1 dispatch for any number of elements in the variant. Now, I looked a little bit around and I found something else, something that you also might have found. This is too small. I admit it. So this is a GitHub repository, Michael Park, or short MPark variant. This is a variant solution that you can just download. Michael Park is a member of the C++ committee, and he has a test implementation that you can now use under the Boost license. So it's pretty easily available. Using mPark variant, the performance is super. It's amazing. Suddenly, we have a performance that is even better than the initial C enum implementation. And especially Clang shines here. It is really amazingly fast. Why? Well, there's a couple of reasons. In the entire code, there's not a single virtual function. There's not a single pointer. There's not a single indirection. Everything is stored in one long vector. All the data is in this vector. You load a cache line, you have all the data available. There is nothing that prevents the compiler from doing aggressive optimization because even the functions can be inlined. This is the perfect setup for performance optimization. So mPark variant apparently works better. But why? Okay, Michael cheats a little bit. I have to admit, he does a switch instead of a function pointer. And okay, he is limited to 32 cases. So if you plan to use this, because it's so amazingly fast, do not plan to use 33 or more types. There's a limit. But I personally feel this is something that in a standard library should also happen at some point. The performance is just so much better. So I expect the performance of Stud variant to increase over time. So in total, I rate this with a 9 with mPark variant. True, I cheat a little, but I think because the performance is so amazing, this is perhaps justified. Now, we have a modern solution for the problem that we want to add operations easily. Now I'd like to have a solution that allows us to add shapes pretty easily. And also for this case, for this use case, there is a design pattern, a classical design pattern. And somebody has named it before. Okay, it starts with an S. I don't recall who said it. Strategy. So now we're here. Strategy, the strategy design pattern. Oh, okay, I forgot this one slide. Okay, forgive me. So this is what I said. So there's no pointers, there's no virtual functions, there's no manual allocation. It is cache efficient because everything is together. It uses values only, no pointers, etc. SRP is fulfilled. There's very loose coupling and OCP. It's kind of a really, really beautiful solution, this variant. In the center, it's just simple. And well, I forgot about this side note indeed. This is the tendency that we now try in the C++ community. So there has been another talk by Herb Sutter, a talk about defragmenting C++. And this is a very common theme in his talks nowadays. He wants to simplify C++ as much as possible. Simplify it from a usage point of view, simplify it from a feature point of view, just make it more accessible to people. And I would also argue that Jason is correct, great C++ is trivial. So here's something else in mind. But indeed, good C++ is simple. The good solutions, that simple solutions are the better solutions. Okay, now we're at the strategy design pattern. So strategy is totally different. In the case of strategy, I'm interested in adding operations at runtime. I want to configure some kind of context at runtime. So again, I rename these things that we see what's happening. So this is a shape. And for instance, I want at runtime configure how draw works. For that reason, I introduce strategies. Strategy itself is some kind of base class. And for instance, here I have a draw strategy that I can implement in various forms. OpenGL strategy, a VTK strategy, a Metal, a Vulkan, whatever strategy. Shape does not have to know about any of these implementation details. So now let's apply strategy to the problem we have. First of all, I start with a base class, the draw strategy. This again knows about circles and squares. This is about drawing only. Now, a shape, the base class, has the virtual translate, rotate, and draw function. In this solution, these functions are not separated, but they will be configured at runtime, as you see in the circle. The circle in its constructor does not just get the radius and potentially other values, but also one of these strategies. Here, this is how you should draw yourself. Potentially, there's also setters that allow you to configure this, not in a simple solution. Translate, rotate, and draw are now implemented, or in this case, draw, to call this draw strategy and to forward the request. Please draw myself. And of course, I also remember the draw strategy as a data member, properly managed with unique pointers. The square class is very similar again, just to have two. I get a draw strategy, I store the draw strategy, and whenever somebody calls draw, I simply forward the request to draw strategy. Now, drawing is as simple as it was before in the OO solution. I just call draw on every other shape. So this is not a problem. Now I just have to provide a strategy, an OpenGL strategy. Why not? I implement how to draw a circle and a square by means of OpenGL, and this will work nicely. And so in the main function, I can now say, well, I need a circle with radius 2, and additionally, please use the OpenGL strategy. How would you rate the solution intuitively? Good? Medium? Bad? Bad. Okay. Okay, you don't like strategy perhaps? This is one option, but there is indeed a serious bug in there. A design bug, of course. Okay, you don't like it. This is something else. Look at this base class again. Is this a good base class from design point of view? Absolutely correct. Every time I add a new kind of shape, I add a new draw function in here. So a draw function for rectangles, ellipses, whatever I have in mind. This means that every existing shape, the circle, the square, have to be recompiled also. This solution is in no way better than the solution that we saw in the very beginning, the enum solution. This is not good from an extensibility point of view. But of course, this is a wrong use of strategy. We should not couple the different kinds of shapes, we should separate them. So I should have a draw circle strategy and a draw square strategy. Now it is working much, much better. This is surprisingly often something that people overlook. They do not see this. Oh, I'm using strategy. And well, let's put these things together. They're so similar. Usually sign mistake. Okay, now I have two different kinds of strategies. And circle gets a draw circle strategy. And of course, the square gets a draw square strategy. Now, they get different things. And so I'm now independent. Okay. Now, of course, I have to implement this twice, but it's very little overhead. The real implementation details were in the draw functions anyway. And okay, it's still the same thing you don't like. I have to give a draw strategy all of them. Now, how does it compare? The goal was to be as good as O programming from the addition of shapes. Well, this works pretty well. But still, I liked it was I liked it easier. I thought it was easier before. Now I have to deal with different strategies also, and there's quite some overhead. Addition of operations now, of course, is not so easy anymore. Same problem as before, so same number. I would rate this with 2. Separation of concerns is actually pretty good, but not as good as the solutions that we've already seen, because still draw, etc., are still to some extent coupled. It's not totally decoupled. Simplicity, well, it's not too bad. But I feel it's a little more complex than this, so 1 point down. Performance. Well, I measured it, and again, we suffer the problem of 2 virtual function calls. The first virtual function call is the draw function in the shape, and a second virtual function call is the virtual function in the strategy itself. So this pays up. You get overhead, and you see that obviously GCC implements virtual functions better than Clang does for some reason. I don't know. So perhaps you like the solution. Okay, I did give you a number. So I rate this with 2. It's a little faster than Visitor, but not a lot. Of course, it's important to be able to add shapes easily, but I would like to do this in a modern way of things. I would like to do this with, well, modern C++. What feature could we use to implement the same thing, but in a much, much simpler way? No, so we're still in the realm of dynamic polymorphism. No. So I'm talking about something that was entered in C++11, added in C++11, a class template called std function. I could actually build on std function. Oh no, because std function is actually nothing but an abstraction of a function. And by that, it acts like a virtual function. It can replace a virtual function. This is what I might like to do here. So I say that a stood function for circles is a draw circle strategy, and a stood function for square is a draw square strategy. The base class doesn't change, so nothing surprising here. The circle changes with regard to, well, it doesn't get any unique pointer of base class. It gets a function object. So here, this is how you draw yourself. And it nicely moves it in place, has it as a data member. It's pretty similar, just a couple of places that you have to touch. Square the same thing, gets a draw square strategy, again a function object, which it stores and calls whenever the draw function is triggered. I again have the OpenGL circle strategy. This time, however, it's not based on any, depending on any base class anymore. It's just a callable, something that I can, again, independently implement by means of the function call operator. Now, very similar to the visited function object, but separated. Circle and square are separate. And I simply pass one of these function objects to pushback. So please, this is how you draw yourself, this is how you draw yourself, and this is what you do. All right. It's very, very similar, yet we can probably now do a little more with it. And this is now the effect of having something that is more decoupled. And let me show you how decoupled it really is. So, this is what you might do. All right. But you might also decide to implement this differently. I'm not depending on any base class anymore. I have the full freedom, the implementation flexibility to actually, for instance, use free functions again. I have a draw function for circle and I have a draw function for square. Now, I would like to dispatch slightly differently. You'll see in a second why. I introduce a draw struct, which is a pretty simple struct. It only has a templated call operator, which takes anything, and it forwards to draw. This little fella here is now something that I pass down here. So no complex OpenGL or whatever thing anymore, but just a draw. Whenever you give me a draw function, I will do my thing. If you have something else, okay, give me this else thing. This is nice. You might not see it yet, but this is actually a really, really nice thing that in the original object-oriented based solution was not possible. Because what we can do now is we can take this draw thing, cut it, paste it at the top. No problem. It's a dependent type, a dependent name. This is working. It doesn't have to know any draw at this point. But if it is known up here, just as a stand-in for a draw function, I can actually use this as a default. So by default, use draw. And of course, the same for square. By default, this is what you should do. And suddenly I don't have to specify anything down here anymore. Still, of course, I have the flexibility to pass any specific behavior I want at this point. The interesting point to note here is I do not specify default behavior. I specify default interface. This is so loosely coupled that I do no longer have to provide an implementation. An interface is perfectly enough. As long as you give me some draw function, I know what to do. Really loosely coupled. This is nice. And so let's take a look at how it compares to especially the, this solution and also the original strategy. It's a little better in terms of adding shapes because it's less tightly coupled. It is easier. And it's also a little easier to add new operations. I don't say this is easy, but perhaps it's a little more convenient, less overhead. Separation of concerns, pretty good. Again, perhaps I could even upgrade this. I really like it. And the simplicity, well, I actually like this too. The code, the usage in the main function looks much, much nicer. I don't have to think about these details anymore, but I have the option to do so. Something I could not do before. Performance. Well, the performance is, okay, not as good as it could be. GCC is particularly bad here. This is kind of the worst thing you get. Clang, on the other hand, is actually not that bad. There's a huge difference between the two stood function implementations. I would actually say that Clang does it properly. Apparently, they optimize properly, and so I get approximately the same performance as the O solution. A little worse, of course. This is pretty cool. There is several more indirections conceptually, but still from a performance point of view, I might get the same thing. So, well, a little worse, but I still can compare it to the original solution. Oh, now, okay. We've now seen one solution that is particularly great for adding operations, one solution that is particularly great for adding, or two solutions for adding shapes. Now there's one more possibility. Once we've realized how the stud function works, we can actually extend the idea. Because at this point, it's not particularly great to have a lot of function objects in one of these things. As long as it's just draw, great. But having function object for every possible function, that sucks. No, but we can extend the idea. And when you can go to another modern C++ solution, we can actually implement stud function ourselves. Not directly, but of course with the idea. So again, I start with a circle class that does not have a single virtual function, no pointers at all. It is just circle. The operations again are nicely separated outside the circle. There's nothing, it's not necessary to have this in the circle anymore. Square is the same. Square does, is very, very simple, and all the operations are extracted. Now, shape. The shape class is now where all the magic happens. Shape is no longer a base class. It's not supposed to be. It's now supposed to be some kind of container. Inside a stud function object, you can store something that's callable. Now, in this class, I want to store something that is a shape. Anything that has a certain number of operations. That I can translate, that I can rotate, that I can draw. The first thing I add in the private part is a struct model. A templated class that virtually takes anything that provides me with a translate function, a rotate function, and a draw function. If you give me something that doesn't have these functions, you will get a compilation error. But as soon as you give me these three operations, perfect. And it stores the t. Now, it would be nice if this is something they could store directly inside this shape. But unfortunately, I don't know t. It's anything. It's seriously anything. A circle and square, but also types that I don't know yet. So for that purpose, I add another little struct called concept, an abstraction. Whereas this is the thing that can be anything, this is now the thing that represents anything, an abstraction. Virtual functions, again, for all the operations, translate, rotate, draw. And this model becomes a concept. This is the thing that I actually can store, the thing that I'm pretty sure that I know, a concept pointer. I can now store virtually anything, as you'll see in a second. Still, I store it in a perfectly abstract fashion. The type is gone. I don't see anymore what I actually store. Hence the name type erasure. I have a couple of operations on a shape also. I can translate shapes, rotate shapes, draw shapes again. These functions, however, only forward to the actual implementation of the thing that I currently store. So I can translate and rotate and draw, but of course the real implementation, the functions of the according type are called. Now the public interface, first of all, contains a constructor that can take anything, and it creates a new model of this anything. This can be a circle, this can be a square, this can be anything as long as these operations are present, else it wouldn't compile. I create a new model, but store it as a concept pointer, and hence the type is gone. I don't see actually what I store anymore. There's a couple of support operations for copying, of course, but this is mostly it. This is the shape class. Now, again, I work with a vector of shapes. Quite simple. I don't have pointers anymore. And this vector of shapes, this object, is something that I just use quite naturally. Okay, draw the shape, also from a language point of view, quite natural. In the main function, again, I create a vector of shapes. I push back different things. And these different things actually, again, can be virtually anything. circles, squares, whatever you have available. Anything that has these operations. I don't see it anymore. And I'm back to something that stores the values directly. Less pointers, no obvious pointers at least, no obvious virtual functions. If you have a new shape, you don't have to derive from anything. You can just put it into this shape thing, so this kind of container, and still you have all the operations. Now, how does this compare? Type erasure. First of all, I believe this is the simplest way to add new kinds of shapes. It's actually really, really simple. I can even add things that I've never seen before. Other people can add things and never have to adhere to any of my interfaces. So adding shapes is now as simple as it gets. Adding operations, again, is harder. However, it is not as hard as the other things, so for instance here, because I do not depend on these interfaces anymore. There's no base class that I have to implement. It's a little easier, not perfect though. Separation of concerns, very nice. All the things do not really know about each other anymore. It is much, much easier to think about or to add an operation. Free functions, node member functions. And so since it's free functions, not part of the class, concerns are pretty nicely separated. From a usage point of view, I think this is pretty simple. I would also rate it with an 8. It's not as simple as variant. This was fantastic, but it is much, much simpler than other solutions too. So, performance. The performance is surprisingly good. This is my own implementation, so, well, all the code that you've seen, nothing else, but it is really surprisingly good. It plays in the realm of the traditional solution, not the OO solution. And so I would rate this with basically the same value. However, okay, this is, we are supposed to walk out. No, okay. So there was a switch here, else you don't see my slides anymore. Thank you. So this is a solution that is interesting because there's no red numbers anymore. Actually, this works pretty well. All right, final comparison. I take the modern C++ solutions again. If you take a closer look at these solutions, the first thing that is obvious is that indeed they're simpler. Pretty high numbers, all in the green area. The modern C++ solutions stress simplicity. They're easier to use, usually easier to implement. They're just more pleasant to use. Then also obvious is that the separation of concern is pretty high. This is something that is usually pretty important. SRP is rated as the most important object-oriented design principle or general design principle. Pretty high numbers too. OCP, meaning either addition of shapes or addition of operations, is also pretty high. Of course, there is no solution that can do both well, and I'm not aware of any such solution, but still, high numbers in the green area. And from a performance point of view, I'm actually not disappointed. It is in the range of the things that I expected. Very, very good for variant, surprisingly good, but not too bad for the other two solutions. So, I'm coming back to the initial question. What is C++? It's a procedural programming language, object-oriented programming, function programming, generic programming. Now, I've seen a couple of solutions. What would be your feeling now? You've seen the modern solutions. Was this procedural programming? Perhaps a little bit. The variant, if you look at Michael's variant, it was actually pretty procedural. Yeah, switch statements, the thing that I used in the beginning. Was it object-oriented programming? Well, a little bit, right? There's a portion of object-oriented here. Nicely encapsulated things, for instance. There is base classes in the type erased problem, for instance, a type eraser solution. It was also base class. Functional programming? Well, now some people would say, yeah, of course, a variant comes from functional programming. But not really. It does not really feel like functional programming. It uses a couple of clever ideas from this. It's inspired, but it's not functional. And would you rate this as generic programming? I don't know. So I do not feel that it's any of these. So the only thing that really makes sense potentially is multi-paradigm programming. But I have also a problem with this idea. I just said it's neither of the above, and now I say it's all of them. Does this make sense? Is this really what we do? We don't do any of these, but all of these? It's kind of difficult. So I'm hard to say it's really multi-paradigm programming. I'm not using all of these paradigms, and now there's nothing left. So is C++ language that doesn't do anything? No, I would say we just do not follow any paradigm anymore. Perhaps we have found great solutions that are not inspired by any of the old paradigms. Perhaps we are on a way to emerge with no paradigm programming. And this is not necessarily a bad thing. We have picked the right things from the paradigms we have gained experience, and now finally we have solutions that just work outside of the good old paradigms. So, to recap, the takeaways. First of all, very important, there is no one-fits-all solution. All of these solutions have merits and they have drawbacks. You just have to pick the one that fits your problem best. Even the modern C++ solutions are no thing that works perfectly. Then, it definitely pays off to understand what this modern C++ really means. It's not using modern features. It's definitely much, much more than that. It is about reducing pointers, inheritance, for instance. This is something that you hear in talks a lot. This is what John Parent in his talk, for instance, mentioned. We want to use values instead of pointers. Yeah, throughout the modern solutions, we reduce the use of pointers, which at the same time, of course, also was a good idea from a performance point of view. And most importantly, I believe, we simplified the code. It was much more simple to use the code. This variant solution is as simple as it gets. The type array solution, in the end, if you ignore the implementation details, was also very, very nice and simple to use. Still, it might be reasonable and beneficial to know about all these program paradigms, to learn their advantages, to learn their weaknesses, to understand what is good about OO, what is good about function programming, and the other advantages. Pick the good ideas. And this is what we've done in C++ to this point. We have picked the good ideas. We've made them new solutions. We've combined them in clever ways. And so don't shackle yourself with thinking about paradigms anymore. It doesn't really work anymore. We have better solutions. And perhaps it's time to finally embrace no paradigm programming. So, thank you very much.